is also possible to summarize the results of our model in a table. And in order to do that, we're going to use the following function. So basically, the function summary from our data, posterior simulated data, and we want to summarize our posterior distribution. So when you run this, you get the following table. I'm not going to be explaining all the columns here, but I'm going to be looking at the ones that are most important at the moment. So the first column is the mean of our posterior distribution. So on average, the constant according to the model is around 3.1, let's say, because it's an 8 over here. And of course we know from our simulated data the real value was actually 3. Yeah, so the mean of our posterior distribution for the constant is actually quite close to what it actually was when we generated our data. Similarly, slope 1, when we simulated data, was 1, and we're very close to 1 in terms of our mean. Slope 2 was -1, and again we're very close to that, and sigma was 1, and we're very close to that one here, on average. But of course the fun of doing a Bayesian analysis is that we're not only going to be looking at the mean, but we're also going to be looking at the distribution of these parameters. Yeah, so there's also going to be a standard deviation. Or another way to look at the distribution is to look at the 95 confidence interval. Yeah, so the numbers in this column, so between these two values, so in this case of the constant between 2.9 and 3.3 is 95% of the mass of our parameter. Yeah, put differently, with 95% probability, constant lies between the values of 2.9 and 3.3. Yeah, so for slope 1 with 95% probability, the value of slope 1 lies between 0.8 and let's say 1.2. Yeah, so that's the way to read these two columns. They give us the, actually the 94. I said I think 95 before. It's the 94% confidence interval. Or it's sometimes called credibility interval in case of Bayesian analysis. Yeah, but the interpretation is with 94% probability, the value of slope 2 lies between -1.1 and -0.7. So I'm going to skip these variables for the moment. And the other important variable that you should be looking at is r hat. And r hat should be close to 1. And in this case, all these values are 1. Yeah, so when it's 1, it doesn't guarantee you that the sampling process went successfully. It's more like a warning. If it's not equal to 1, there may be problems. And if it deviates from 1, basically what it captures is that there is zero correlation between the different samples that were drawn out of the posterior distribution. Yeah, so when it's, let's say, 1.1 or 0.9 or even lower, it basically tells you that there is something wrong with the sampling process in the sense that we're not, as we explained over here, we're not randomly running over the whole interval of the posterior distribution. Yeah, so usually when r hat is not equal to 1, it sort of corresponds to the fact that you have zero correlation here, and not this random zigzagging that we talked about before. Yeah, so when you summarize your parameters, for this course, the columns that we're going to be interested in are the mean and standard deviation, and from these we can derive this credibility interval, and we're going to be worried about r hat, which says something about how serial correlated the sampling process was. Then finally, one other thing you can do to sort of check what your model has done is to look at the predictions of your model and compare these to the observations that we actually have. Yeah, so in this figure, what you see is the red dots. These are actually the observations. So this is the data that we generated. And you see these sort of lightish blue lines, and they give you the intervals where the model predicts that these values should lie. Yeah, so the figure on the left plots our data as a function of x1 against y, and the figure on the right does the same, but then as a function of x2 against y. Yeah, so our model has two explanatory variables, x1 and x2. So the other way to plot this is in 3 dimensions, but that's usually not particularly informative. So just to see how the figure works, so first we take the percentiles. Yeah, so from our simulated data variable, we look at our predictions for the observable variable, and here we take actually the 95% interval. Yeah, so we take the 2.5 and the 97.5. So in between those two values lies 95% of the mass for that parameter. Yes, you can check the shapes of these of this variable to understand why we choose x is equal to 0 here. So we're looking at the columns, and then we're transforming this using this t. Yeah, so we switch basically columns and rows. We generate our figure, and we do that with 2 subplots. So we specify here one row, so that's the one here. The 2 here basically means that we are going to have 2 columns. Actually, perhaps for this video we can change this to 20, and I'll make this 10. Let's see whether that gives us a bit. Yeah, so that as a picture is slightly clearer, I think. Perhaps I think I should increase this to make it, to increase visibility a bit. Yeah, I think that helps. So on the horizontal axis we have for our data different values of x1 that were generated by our data. And so here we have a data point where x1 is equal to minus 3.2, let's say, and y is actually close to 0. So that's what the red dot here means. It's the actual observation. The blue line indicates that when our model is going to predict where this point lies, it's going to say with 95% probability this observation is going to lie between the top end of this line and the bottom end of this line. Yeah, so this here covers 95% probability. Yeah, so as you can see, most of these red dots are actually somewhere in this blue line. Of course, not all of them. So for instance, here you have an exception where the red dot is above this line, which is correct because it's the 95% probability interval. So sort of 5% of our observations shouldn't lie on this blue line. The thing that you observe is that, when you would sort of do something similar with OLS, you would see that these predictions would sort of form a straight line. But that's not the case here, because for each value of x1 that I have here is a corresponding value of x2. Yeah, so I think the parameter on x2 was negative. So let's say this point over here, which is on the low end, which is rather low, so it's likely that this value of x1 in the observation corresponded to a rather low value of x2. Yeah, so that pushes the blue line up. Yeah, so that pushes my prediction up, and which makes sure that the observation is actually on the low end of this predicted interval. Yeah, so you can sort of see as upward sloping line through these blue lines. Yeah, which sort of corresponds to a slope equal to 1. That's actually in the data. But there is some randomness around this, because for each observation, the blue line is not only calculated for this value of x1, but it's this value of x1 combined with the value of x2, which I cannot actually see in this figure. Yeah, so that's why this relationship of the blue lines is not sort of smoothly a straight line with slope 1. Yeah, because each prediction is affected both by the value of x1 and the value of x2. Yeah, but this plot where we plot the predictions together, so the predictive intervals, so the 95 prediction of the interval where this observation should be, together with our observations, gives us an idea of whether the model that we're estimating here makes sense. Yeah, so for instance, if all the red dots would be way above or way below or all on the lower end of these predicted intervals, that would be an indication that our model is actually not doing so well.